Hello and welcome to another video. In this video we're going to be working on add one row to tree. And in the problem you're given a root of a binary tree and two integers val and depth, and you want to add a row of nodes with value val at the given depth. The root is at depth 1. And so basically the idea is if the depth is 1, then you want to just add that value at the top and make the root its left child. So if the depth is 1 and the value is 1, you would just say, okay, let me just make a node of 1 and then this, and then I'm done. Then I should return this thing. That's what they tell you here. Otherwise, depending on the depth, like let's look at these examples that'll make it pretty clear. So if the depth is 2, basically you're saying at the second level for every single node, like for every node above this level, so let's say this is level 1. For every node at level 1, because the depth is 2, instead of having its children, give it children of the value, and then take its left and right original children and make those the children of this value. So its left child used to be this, and its right child used to be this, but now instead replace those with the value, and then make the left child of the value the node's original left child, which is this, and then the right child, the node's original right child. And that's basically it. So it's actually not too hard to do this. So same example here, so depth 3, so this is like level 1, 2, 3. You basically are saying, because the depth is 3, I need to take every node at level 2, take its original children, replace them with these values, and then make the left child of this value the left child that used to be the left child of the node, and then the right child of this value, the right child that used to be the right child of the node. So it's actually pretty easy, and we can actually just do this recursively by keeping track of what level we're on. So we can just say, like, if we're on, like, the level we need to be on to add these children is depth -1, right? So if this is the only one that matters. So if we're not on depth -1, we can just recurse. And I think I said this earlier in problems. You can just do a recursive DFS for almost all these tree problems until you need to do a BFS. Or recursive DFS is like way easier. So we can just say, like, let's walk through some of these examples, I guess. Let's walk through this first example. So we'll be on, and let's write down the levels. So this is level 1, level 2, level 3, and we can just pass down the level in the recursive function. So we're going to start here, and then we're going to say, okay, we're on level 1. So we don't need to do anything here, or actually, no, we do need to do something, because we're on the level that's the depth -1, right? So for every node that's on level 1, we need to save its left and right child in the variable. So we'll save its left and right child in a variable. And then we need to give it a left child of this and the right child of this, right? So give it two new children of these two values. And then you make the left child of its new left thing equal to its old left child. And then you make the right child of its right child its old right child. And then you can just return, right? So once you add these things for the node, you don't need to recurse further. So essentially we take the node, we save these two things in a variable, and then we give it children. And we can actually demonstrate it easier with a picture of a tree. So let's say we have this tree. And let's say we are manipulating this node here. Actually, let's make a bigger tree to make it easier. So let's say we have this big tree, and we are manipulating, and let's say this tree doesn't have a right child at all. So let's say we have something like this, and this is the node we're manipulating here. So let's say this is level 2, and the depth we're looking for is 3. So essentially we're trying to add a node here. And let's show what that would look like essentially. And let's say the value we're trying to add is like 3. So what would happen is whenever we get to a node that's on level 2, so like for this node, we are going to save its left and right child in a variable. So we're going to save this in a variable and save this in a variable. Yeah. So picture might not be the best, but it's okay. So get rid of this, get rid of this. So these two are saved in a variable now. Now we give it a left and a right child of this value. So 3, 3. Then we say, okay, let's take its left value that we added, this 3, and make that node's left child this left value that we saved in a variable. And let's make this node's right child the value that we saved in a variable. So this left child is going to be here, and this right child is going to be here. And then we don't need to recurse anymore, so we're just done. And if we're not on the right level, then we just recurse further down. So like when we start at the root, we're only going to be at level 1, and we only care about nodes at level 2. So we'll recurse down here, do this little addition, recurse back up, recurse over here. Now we have to do an addition here. So here, the left child is this, so we save this in a variable, get rid of this. Its right child is null, so there's nothing there. Now we add these two nodes again, 3 and 3. And then we make the left child of the left 3 the node's old left value, so that's going to be this. And then we make the right child of this tree the node's old right value, which is just null, so this will be null, and then we just return. So that's kind of the idea. It's pretty simple. All you do is keep track of a level, and then whenever you're on the level right above the depth, you just add these two values, and then you put the left and right child of them correctly, and that's basically it. So yeah, and same thing here. If you look, if we're on depth 3, we need to get to level 2. Once we get to level 2, we save these two nodes in a variable, or in two variables. We add these two children, and we make the left child of this node's old left, and we make the right child of this node's old right. That's basically it. Then we just return. So we don't need to like keep recursing. We just stop at the level that we're at, or the level right above the level we're at, I guess. Yeah. Okay, so let's do that in Java. So you might be able to do this in one, or especially in another language, you might be able to do it in one function. I'll just make a helper function like I always did in all these tree problems. So the only thing we need to maintain is the depth, right? That's what we need to pass down. We don't need to return anything. We're just going to rearrange our tree and return the root. So this can be void traverse, and so we need a node. We need the value that we're going to be putting in. We need the depth. So these are just from before, and then we need the level. And so the node can be null, like I didn't show in this picture, but let's say the depth is like 5 and our tree looks like, or the depth is something big, but then our tree doesn't have a left child or something, or it doesn't have a right child, right? So you can easily get to a null node here. So that's the first thing we'll do. So if we get to a null node, we'll just return. So if node equals null, let's just return. So then the next case is if we are on the depth we want to be. So if level equals depth minus 1, right? Because if this depth is 3, we want to be on level 2 to make the changes. So this is the case. In that case, we're going to store the left and right children of the node in a separate variable because we're going to replace them. So we can say like tree node left equals node left, and tree node right equals node right. And if they're null, it doesn't matter, it'll work fine. So now we have to give our tree node a left and a right of just this value. So we can do that, and we can pass this into the constructor. So we could say node left equals new tree node. And if we actually look how this function is made, so it takes a value, which would just be val, and then it takes a left tree and a right tree that can be its children. So this new left that we made, its left needs to be the original left, so we can pass in left here. And its right needs to be null. And same thing for the right, so node right equals new tree node. It takes a value. The left now is going to be null, and the right will be its old right? Because if we actually look at this picture, so this new left thing's left is going to be the old left, and the right is null, and this thing's left is null, and its right is the old right. So that's why it's like this. And that's all we need to do. And then otherwise we just recurse. So if we're not on the right thing, we can just recurse. So we can traverse node left, value, depth, those stay the same, and then the level just increases by 1. And same thing for the right. So traverse node right. And yeah, we don't need to return anything. So we're just going to modify our tree. Like we'll start at the root, we'll modify our tree, and then we have access to the root in our original function, so we can just return the root. So this can be void. And here, we do need the other check. So like I said, if depth is 1, then you basically just want to make a new node, and its left should be the root, and then you just return this new node. So we'll check for that in our original function. So if depth equals 1, we are just going to return a new tree node with a value of val. Its left will be the root, its right will be null. And we return that, and then we're done. Otherwise, we want to call our function. So we can call traverse on the root with val, depth, and the root will be at level 1. and we can just return the root. So we'll modify the tree in this function, and then we'll just return the root. We don't need to like pass back anything, and we don't have any like global variables or anything, so it should be fine. All right, and there we go. So it does work. Okay, so as far as space and time, let's take a look at these values. So depth can be depth of the tree, worst case scenario, and all this stuff is whatever. Okay, so if depth can be depth of the tree, worst case scenario, we're going to be going down to like the second to last level, which is basically O of n. Especially if our tree looks like this, right? Same kind of thing again. So if our tree looks like this, and let's say this is like 1,000,000, our level can be, you know, like million, in which case we'll basically just go down all the way. So that's O of n time, worst case. So we might have to visit every single node, or almost every single node, which is O of n, and space, same thing, because, so I guess you can argue, yeah, so I guess you can argue that the space isn't O of n, it's O of the depth, right? Because the space here, like we don't have any like variables we're storing other than the recursive stack. So even if the tree looks like this, if our depth is like 3, we're only going to go down to here. So the most we're ever going to recurse down one level is the depth, right? So that's what it depends on. So it doesn't depend on n, it depends on the depth. So depth. And n is like the number of nodes in the tree. So I'd say it's like this. And that is generally the space. Technically, that is the space for all tree problems, right? It's the depth of the maximum depth of your tree, but you can have an O of n depth. But in this case, because you actually have a variable for the depth, it only depends on the depth. And yeah, I think that's going to be all for this one. So once again, as you can see from if you've been following these problems, same kind of template, just make a traverse template, figure out what you need to pass down, what you need to return, and that's the easiest way by far. If you want, you can do this with a queue, with BFS or whatever. I think recursive is just way easier though, so usually I just try to think of a recursive solution. And honestly, these medium tree problems should take you, like, if you've done enough, should take you like 5 minutes, and if you can't come up with a recursive DFS solution, then start looking into breadth first search. But as a default, DFS is way, way easier for trees. It's like easier to visualize, easier for everything. And I use BFS for basically everything else. So for like graphs and all that, shortest distance and all that, I usually use BFS because it's way easier for that. So yeah, it's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.